Hi, welcome back to Foundations for Machine Learning. This is the start of a new module consisting of 4 lectures on ways to make gradient descent much better in machine learning. So specifically, we'll be looking at something called stochastic gradient descent, momentum, RMS prop, meaning root mean square propagation, and Adam optimizer, which is probably the most famous optimization algorithm in the entirety of machine learning. I initially thought of recording all these 4 into one single lecture, but later decided that that might make the lecture too long. So I decided to split this and go into depth of each of these individual topics, which gives you a fairly good intuition about why people thought of certain ways in which you can make the gradient descent algorithm much better. So we'll be looking at stochastic gradient descent in this lecture. So I have divided the lecture into 2 parts. In the first part, I'll be discussing the theory of stochastic gradient descent. And in the second part, we'll be implementing this and we'll see why exactly stochastic gradient descent is better than the normal vanilla gradient descent. The normal gradient descent is also called as batch gradient descent because you are using the entire batch of data set to decide by how much you should change the parameters. Now, you might be wondering, okay, I don't know what is gradient descent, so should I follow this lecture or not? So don't worry, we'll be doing a proper recap of the gradient descent itself in the first part of the lecture before moving into the stochastic gradient descent. So let's get into the lecture. So gradient descent is an algorithm for minimizing your loss function or cost function. The loss function or cost function is an index of how far your predictions are. If you have a machine learning model, how far away your predictions are compared to the real data. So that is what the loss function is. And in the last lecture, we had discussed that if we have a linear regression, then the loss function can be described as an average of, so if these are the data points, and if this is the straight line that describes the linear fit through these points, then loss function can be described using something called mean squared error. And then mean squared error is 1 by n, where n is the number of points, sigma I equal to 1 to n, times predicted value of y. So it is written as yi cap minus actual value of y, the whole square. You can also write it as y minus yi cap, yi minus yi cap, the whole square. So this is called as mean squared error because there is square and there is square of error and there is mean because you are doing summation and you are dividing by n. So we saw that this is an example of a loss function or cost function. In gradient descent, our singular goal is to minimize the loss function, which only depends on the model parameters. So here in this example of linear regression, the model parameters for the straight line are the slope and intercept. So basically yi bar equal to mxi plus c. So m and c are the parameters which can be collectively called as theta, which determines what the value of the function, the loss function j, or the mean squared error MSE should be. So what we do first is we initialize, the first step is to initialize some random values for this theta, which are the model parameters. In the last lecture, we initialized theta with values of 0 for intercept and 0 for slope. Any random values are fine. Then you change the value of theta by a certain number. And how do you get that number? So this is the value by which you decrease theta. So here there are 2 terms. First, eta is the learning rate, and this grad operator is taking gradient of j, which is a function of theta with respect to theta. So it's like gradient of j with respect to theta. So it's a gradient of loss. But we are not ascending the gradient because let's say the loss function j is a quadratic function with respect to theta. So let's say this is j and this is theta. Assume that your j looks something like this. Then you are not ascending. You are not going in the direction of the slope. You have to go in the opposite direction of the slope to find the value of theta, which kind of minimizes the value of the j, right? So that is why it's called descending, gradient descent, and that's why you have a minus sign here, because you are modifying the value of theta such that you are moving opposite to the direction of the gradient of the loss function, right? So the step 1 is initializing the parameters with random values. Step 2 is calculating the gradient. Step 3 is updating the parameters. So here the new value of theta. So here you can also put like a subscript called new is old value of theta minus eta times gradient of the loss function. Then update the parameters and repeat these two steps 2 and 3 until you reach some sort of convergence, or for a predefined number of steps. You can do this 100 times, 1000 times, whatever the computational power of your system allows. So this is a brief recap of gradient descent. However, this way in which you are trying to optimize or minimize the loss function has certain issues. Firstly, if your data set is very large, just look at this gradient descent. You have to perform a large number of calculations. Firstly, you have to calculate the predicted value of y for every single input data points, and you have to compare it with the actual value of y. Then you have to do sigma summation of difference between prediction and the actual value, and take mean squared error. And not just that, so this is just to calculate the mean squared error. You have to calculate the gradient of the mean squared error with respect to the parameters. You have to update the parameters and do this 100 or 1000 or how many ever number of times you are satisfied for obtaining some sort of convergence. So this is very computationally costly. Then convergence can be difficult in noisy loss surfaces. And what do we mean by noisy loss surface? Noisy loss surface can look something like this. So let's say instead of a beautiful loss function like this, so this is j and this is theta, let's say it looks something like this. This is a very noisy loss surface, and it's very difficult for the gradient descent to find a proper convergence at some good minima. So this is also an issue with the vanilla gradient descent. So vanilla gradient descent is exactly same as gradient descent. GD is same as vanilla GD. So whenever you hear vanilla gradient descent, you imagine gradient descent which is done normally. It's also called batch gradient descent. And why is it called batch gradient descent? Because you are calculating the mean squared error for the entire batch of data points. So here if you have n data points, you are calculating the mean squared error for this entire batch, and when you take the derivative of mean squared error, you are calculating the gradient such that the contribution of every single data point is coming into the gradient. So this is called as vanilla gradient descent. So there are a few ways in which we can make the gradient descent better, and the whole idea in this series of 4 lectures is to learn in detail what are those different ways. So in this series of lectures, actually we'll not be learning 3 ways, we'll be learning 4 ways in this series of lectures. We will learn 4 ways to make gradient descent better. So this lecture will focus just on stochastic gradient descent. The next lecture would focus on something called as momentum. It's a concept which has fairly good intuition present from physics itself. The lecture following will focus on RMS prop, which is root mean square propagation. And final lecture in this series will be on Adam optimizer, which is the most famous optimization algorithm. So let's look at method 1 in detail in this lecture, stochastic gradient descent. So in regular gradient descent or in vanilla gradient descent, what we do is the new value of theta is equal to old value of theta minus learning rate times gradient of the loss function. Your loss function could be mean squared error, it could be anything else. There are many types of loss functions. It could be cross entropy loss, it could be log loss, whatever it is, depending on your problem. This is the regular gradient descent, and we know that. In stochastic gradient descent, what we do is everything is same, but when we calculate the value by which you have to modify theta, you will not take a mean of all the different data points to calculate the mean squared error, but rather you will just take the square of error for one random data point. So imagine that this random data point is I equal to 3. Then for I equal to 3, if your theta is such that m equal to, let's say, 2 and c equal to 1, and let's say if I equal to 3, maybe xi, your data set could be something like this. So x equal to 1, 2, 3. So this is 1, 2, 3. So and this could be 1, 2, 3. So if I equal to 3, then xi equal to what? Xi equal to roughly 3, and yi, the y corresponding to this particular I, equal to 3. It's also 3. And then what is yi cap? Yi cap is nothing but mxi plus c, and that is m we have assumed to be 2, c assumed to be 1. So 2 times 3, which is 6, 6 plus 1, 7. Now this gradient would be gradient with respect to theta, right? So it will have two components, dou by dou m and dou by dou c. So we can calculate dou by dou m of what is this, yi minus yi cap the whole square. Yi is mxi plus c, sorry, that is yi cap. It doesn't matter, the order does not matter because you are taking the square, but maybe I can write this as the second item. So yi minus mxi minus c, and dou by dou m of this square equal to 2 times yi minus mxi minus c times minus xi, right? So this is how the dou by dou, like gradient theta of just this expression will look like for a random value of I. I randomly selected this I. The summation is not coming. If we were doing the vanilla gradient descent, you will be doing a summation for all values of I instead of just this random value of I. Now you might be wondering, how exactly is this helpful? This is particularly helpful if you have a big data set and you don't want to calculate every single time, you don't want to calculate the parameter update value using every single data point. Because imagine that you have something like this. You have a data set which looks something like this. You have bunch of data points here, then you have bunch of data points here, and you have another set of data points here. Now an ideal model, a linear regression model, which is supposed to learn patterns from this data, will go through the data something like that, looks something like this. Now the problem with vanilla gradient descent is that since there are 3 clusters to the data set distribution is not very uniform, it's clustered. You don't need to do gradient descent using this point, then using this point, then using this point, this point, this point, etc. Even if you have just one of the points as a representative of this cluster, it's enough. Then you need another point as a representative from this cluster, and maybe another point from this as the representative of that cluster. With that itself, you can get a fairly good fit through these data points. But in vanilla gradient descent, every single point you have to consider every single point in calculating the gradient. But in stochastic gradient descent, maybe initially you randomly select let's say this point for calculating the gradient, but since the selection of the next point next time for calculating the gradient of the loss function is random, you may end up randomly selecting a point from this cluster anyway. So you are not kind of repeating the calculation of the gradient of loss with respect to parameters by unnecessarily considering all of these points into consideration. So the stochastic gradient descent is very helpful if you have data which has kind of redundant information available. So it can help you avoid this redundancy and converge faster. Now you don't have to trust me when I say convergence is fast, because you will see that when we are implementing this in code, right? So this is needed exactly, for example, if you have 1000 parameters. So here we had 2 parameters, slope and intercept, and we had 3 or 4 data points. But imagine you had 1000 parameters and 1 million data points. Now if you have 1 million data points in vanilla gradient descent, for every single time step you are calculating the summation by calculating the value of output for every single one of the 1 million data points. And then since you have 1000 parameter to update, for updation of every single parameter you are using the data from all the 1 million data points. So eventually you are doing a huge set of calculation. But in stochastic gradient descent, for every parameter update, you calculate the gradient only using one random data point from these 1 million data points. So you significantly reduce the order of magnitude of the number of calculations that you have to do by one by millionth, because if you have 1000 parameters and if you are calculating the gradient using all these data points, now you are just using one random data point to calculate the parameter update for every single of the 1000 parameters. So that is the advantage of stochastic gradient descent. Now faster update, the reason why this is faster is because you reduce a lot of redundancy. This will be visible only for large data sets, by the way. For very small data sets, probably stochastic gradient descent is not good. You need to consider all the data points to capture all the patterns from the data and to appropriately modify the parameters during the iterations. And one more thing is, when there are frequent updates, you may, for example, if you have, imagine your loss function is something like this. Now in a vanilla gradient descent, if you start from here, you will come here, you will come here, 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 and maybe you will settle here. Whereas the global minimum might be somewhere here. In stochastic gradient descent, what is done is, let me erase all of this. Let me draw this. In stochastic gradient descent, you may start from here and you will calculate the current value of the next value of theta, and you will end up reaching here. But to update now, you will not be taking all the values of theta into consideration. All the data points into consideration. You will only consider some data points. So it may so happen that you are now, instead of going down this slope, or if you are starting from here, it may so happen that instead of you going down this slope, you may end up going in this direction, and then you may be able to break through this point. You may reach here. Sometimes you may come back up. I will show you a GIF animation after we code the stochastic gradient descent, that the direction of movement is not always down the slope, because the value of the parameter update will entirely depend on which random data point you are picking. So here, this is not x, these are here the x-axis. I am assuming this to be theta, and this is j of theta. Okay, and in stochastic gradient descent, you may be moving slightly randomly, but eventually you have a higher likelihood of finding not getting trapped here and finding this particular global minima. And you may be able to escape saddle points also. So saddle points are points like this. Not like that. Points like this, where the slope is 0 actually. So if slope is 0, what happens is, when you have, so this is neither local maxima nor minima. Maybe minima is over here, right? So here also slope is 0, here also slope is 0. The difference here is like the slope when you approach from left hand side and slope when you approach from right hand side is such that the second derivative is not similar to the second derivative when you are looking at a minima like this. So in saddle point, if you end up getting stuck in a saddle point, then the gradient will be 0. Gradient of j with respect to theta will be 0, and you will not move anywhere from here because the parameters won't get updated. So, but if it's a stochastic gradient descent, even if you end up at this part of the loss function, the value by which your theta will get updated is not dependent on the slope of gradient of theta, gradient of j with respect to theta for all the points. It is only gradient of j with respect to theta for only some random xi and random yi, or xi and whatever else is the input parameter, x1i and x2i. So you can escape the saddle points. Now the only issue is that there will be noisy convergence. As I mentioned, you will not be going in a unidirectional manner. I will show you this as a proper GIF animation. There is also one more variation for the gradient descent. So this is the vanilla gradient descent. And this is the stochastic gradient descent. And vanilla gradient descent is also called as batch gradient descent, so the normal gradient descent. Then there is one more thing called mini batch gradient descent. So mini batch gradient descent. Here, instead of just taking one random point like how stochastic gradient is implemented, you will be taking a subset of points for calculating the gradient. In vanilla gradient descent, you are taking all points to calculate the gradient. In stochastic gradient descent, you are taking one random point. In mini batch gradient descent, you are taking a subset. Now, what we have to do is we should implement all of this to believe or to understand what the stochastic gradient descent looks like in practice. So let us now implement the stochastic gradient descent and batch gradient descent for a particular data set, and let's look at what is the difference in the outcome. And we'll be doing this in Python, and I'll first walk you through the code line by line, and then only we'll be implementing. Okay. So the first step is we import the required libraries. So NumPy for working with arrays, matplotlib for plotting the images or plotting the graphs, time for basically we want to estimate how much time it took for us to execute the code for certain number of iterations for stochastic and batch gradient descent. The next set of the next block of code that I have written. So by the way, I have already implemented this code. I just wanted to make sure that the code is working. So I have already implemented this by running every single block of this code. But before running this on Google Colab, I just wanted to give a run through so that you also know what each block of code is doing, right? So that's why I'm giving this walkthrough through the code. So the second block is generating some synthetic data. So in synthetic data, what we are doing is we are assuming that the data set is looking something like y equal to 3x plus 7 plus some kind of noise. So 3x plus 7 would look something like this, a line with intercept at 7 and slope of 3. And but the data points are not created along this line. The data points are created something like this with some noise added to this equation, right? So to add the noise, we are using this np.random.randn. So we are creating several set of numbers, random numbers, and we are adding a random number to y equal to mx plus 3 equation. And this np.random.seed is acting as a initial number which will help us have reproducible results even if we are using a random number generator. So if seed is kept constant, this np.random.random output of this random number generator will be always the same. If the seed is not provided, the output will vary. All right. Now, definition of mean squared error. So we are using linear regression. So mean squared error is the best loss function to use. It is simply the mean of true value of y minus predicted value of y square. And we are just defining this function, that is this block. Now let's go through the block of the normal batch gradient descent or vanilla gradient descent, right? So we discussed that vanilla gradient descent or batch gradient descent is exactly same as the normal gradient descent that we have been talking about. It is not stochastic gradient descent. It's gradient descent where nothing special is done. So here we are defining the function where we pass the x values and y values, data points. Then epochs is the number of times we are doing the iteration of modification of the slope and intercept values. LR is learning rate. So we are starting with learning rate equal to 0.01, and of course we can try and modify this. So m comma n equal to x dot shape. So this will allow us to understand how many data points are there. Now in this line of code, this bias term is added so that we can represent the whole thing of calculating the prediction as a matrix multiplication. Because let me jump to this line of code once. Predictions equal to x dot of theta. Basically what we are doing here is imagine that your input values are x equal to 1, 2, 3, 4 and output y is 7, 8, 9, 10, and this can be ideally approximated using some equation mx plus c, right? Yi equal to mxi plus c. Now if you want to represent the whole thing as a matrix multiplication, you can append a series of ones. So 1, 2, so x, the new x will be the old x, which is 1, 2, 3, 4, plus a series of ones appended as another column, and then theta would be the values of the parameters, which is so now this is like a 4 by 2 matrix, so you need a 2 by 1, so theta equal to m and c. Now you can say that the prediction y predicted equal to x times theta, because x is left like a 4 by 2 matrix and this is a 2 by 1 matrix, so the result of x times theta will be like a 4 by 1 matrix, and each prediction will be, the first prediction will be, this is equal to 1 times m plus c, so this first one will be m plus c, second one will be 2m plus c, third will be 3m plus c, etc., and then last one will be 4m plus c. So if you append a series of ones, basically with just one multiplication you can do the y equal to mx plus c formula with just a matrix multiplication for all the data points. So that is what you are doing here. You are appending a series of ones in this line of code. Then theta, we are starting with initial random values of parameters. So theta is your parameters. In linear regression it's simply slope and intercept, and you are starting with a empty array for storing the losses in every single iteration. So first you make a prediction using the matrix multiplication x times matrix theta, and then the error is nothing but the difference between prediction and the actual value of y. Actual value of y you are passing into the function over here. Now the gradient is 2 by m times x times t dot errors, so this is also fairly easy to understand. So in mean squared error, MSE equal to 1 by n times sigma y predicted minus y actual, maybe I can, yeah, y predicted minus y actual square, and this is equal to 1 by n times sigma y predicted is nothing but mx plus c minus y the whole square, right? Now if you want to get the gradient with respect to, let's say, m, then dou mean squared error by dou m equal to 2 by n times, okay, I guess here if you write 2 by n times x times sigma mx plus, or rather I can write mx plus c again as y predicted minus y actual the whole square. So and then in dou mean squared error by dou c it will be 2 by n times x won't be there, so this x won't be there because x was the coefficient of m. For c the coefficient is 1 times yp minus y predicted minus y actual the whole square. So that is what is calculated here. Where is that? 2 by m times x times t dot sorry, this is not x times t, x transpose times dot of errors. So dot of errors is this, okay, square is not there by the way, because when you are taking derivative square will be gone. So this is the dot of errors. So you are taking the product of x transpose and the matrix where the prediction minus actual value of y is stored. Then you are performing the theta updation, and look at this, it's minus equal to, which means you are doing theta equal to theta minus learning rate times gradient, which is the formula for the gradient descent. And finally here you have a function called compute loss, which we had written here. The loss is nothing but the mean squared error np dot mean of y true minus y predicted square. So this will compute the loss, and you are now storing the loss in the empty array. So you are appending, so the length of the array will keep on increasing after each iteration. Then this batch gradient descent, which is vanilla gradient descent, will return two values, the theta where the slope and intercept are stored, losses which are which is the array where you are appending the values of loss in every single iteration. In stochastic gradient descent you are doing pretty much the same thing. You know, you are calculating the length of the number of data points and the number of features in each data point. You are appending by ones, you are assigning random values to theta at the start, you are having an empty array to store the losses, and initially for each epoch the loss is 0, and what we are doing here is random index equal to np.random.randint. I had to pause the video because I noticed a small issue with the code that I had written here, but basically you are starting with the random. Okay, this random index is the which data point are you picking for calculating the gradient. So you are picking a random index between 1 and m, where m is the number of data points, and then you are saying the data that point that you are taking is corresponding to it's taken from the mth or this random index from the input set, which is x, and from the output you are taking the corresponding actual value of y, which is yi, and predictions is xi dot theta, xi dot the theta, where theta is the appended value, sorry, x is the so here actually xi is taken from x of some random index, right? And if you look at the random index, how does it look like? It looks like this. It has two values, the appended value 1 and the original value whatever xi was. So xi will be, in this particular case, it will be 2 and 1, and then you are multiplying this with the theta matrix, and theta will look like m and c, and then when you do the multiplication xi times theta, it will be nothing but 2m plus c, right? So that is what we are doing here. Xi dot theta, then error is nothing but predicted value of y minus yi itself, and gradient same formula as before, then theta equal to theta minus learning rate times gradient. That's why this is minus equal to, and just one thing I have to correct here is this is not loss plus equal to, it's simply loss equal to compute loss. So compute loss function will compute the mean squared error, where yi is the actual value of y and predictions is the predicted value of y, and then we are appending the value of loss to the losses array. All right, now we have two data sets. We'll be defining a large data set and a small data set, and then we'll be generating data with large data with this many number of data points, 1000 data points, as well as I think this is what, 1 million or 10 million. I think this is 10 million. So these many data points, we can play around with these numbers. We can start with this and we can play around with this. And so we'll be generating x values for just 1000 points and corresponding y values, x values for these many points and corresponding y values. And then we'll be performing first batch gradient descent or vanilla gradient descent, and we'll be doing it for small data set as well as for large data set. So here is where the time parameter is coming, because I just wanted to keep track of how much time it takes to run the batch gradient descent and the stochastic gradient descent. So here we have the start time, and then here we have the final time, the time that was taken equal to time at that point minus the starting time. And we will be computing the losses for the batch gradient descent first for the small data set, and then the batch gradient descent for the large data set. And what is this batch gradient descent? It is the function that we had defined here over here, this function. All right, and epochs we are defining to be 50. We can change this also. Learning rate we had defined as 0.01. This also we can change. We are not passing this as a parameter from the place where we call, but it is one of the arguments that we are defining to be 0.01. Then we also have a similar thing for stochastic gradient descent. So for small data set and large data set, so we will first note down the initial time, then the difference will be the time after finishing the run minus the starting time. We will do that for large data set also. So stochastic gradient descent function is called with small data set with the small x and y input and corresponding y values, and also the large input and corresponding y values. And then finally we will be printing the time it took for the small data set and large data set for both batch and stochastic gradient descent, and we will also be printing the losses, the final loss. Okay, and then so that is this line of code. I hope you are understanding this is a fairly straightforward code, so that's why I'm not spending too much time on this. Then finally we are plotting the losses for large data set and small data set to compare batch for both data set. What is the difference in the loss for iteration wise for batch gradient descent and stochastic gradient descent? So this graph should look something like initially the loss is large and then it's small. So this is iterations or epochs, and this is loss, and we will have two curves. One curve will correspond to batch gradient descent and one curve will correspond to stochastic gradient descent, and there will be one such plot for small data set, and there will be one more plot like this for large data set, right? So this is the expected output. So I think that is enough. We can now start writing the code. So instead of writing all of this from scratch, which will just elongate the length of the video, I can just copy paste from here because I have already written the code. And if you want to write from scratch, all you can do is, like, you can pause the video, write the code yourself and see what each block of code is doing. So I'll be implementing this code in Google Colab, but feel free to use Jupyter Notebook, whatever environment you are comfortable with. I have already opened like an empty Google Colab notebook here, and we can bring the code here. So first let's bring the library import part. Import numpy as np, matplotlib as plt, matplotlib.pyplot as plt, and import time. Then next is defining the synthetic data set. So at this moment when we run, nothing is going to happen because we are not calling the function, we are just defining it. Then defining the compute loss function for calculation of mean squared error. Then implementation of the vanilla gradient descent, aka batch gradient descent. These are all function definitions, so nothing is going to happen when we run this part. Then implementation of stochastic gradient descent calculation function. Then the part where we define the actual data set, because here, although we had this function for generating the data, we did not call the function yet, right? So here is where we are calling the function to create large data and also to create small data, just by saying the number of data points that we want. Then okay, so here now something has actually happened because the data set has been created. Now we are running the batch gradient descent first. So let's run this part for large data set and small data set. Then we will run stochastic gradient descent for large data set and small data set. Both of these blocks of code will take some time depending on the size of the data. And now let's print. Yeah, it actually got implemented reasonably fast. Now before plotting anything, I just want to see how the loss looks like. So here we can see that for large data set, the final loss in stochastic gradient descent is actually higher. And if we were to plot the loss as a function of epochs, you can see that batch gradient descent is blue, stochastic gradient descent is the orange, and there is difference in loss. Perhaps maybe what we can do is we can increase the size of the data set, but surprisingly for some reason the small data set has lower value of final loss. It's very, very surprising. Not sure what exactly is going on. Theta equal to, I think all of this is fine. We are computing the loss. Okay, what if my data set was even bigger? Let me run all. If it was even bigger, perhaps my thinking is that the bigger the size of the data set, the better the stochastic gradient descent should be. Okay, probably not from a loss point of view, but because yeah, for sure, loss stochastic gradient descent is not as good as it's much more noisy than the vanilla gradient descent. But from a time point of view, execution time point of view, stochastic gradient descent should be much faster. So let's at least compare the time before we look at anything else. Yeah, I don't think it's fair to expect the loss to be smallest, but let's see what's happening after this run finishes. Alright, so we have finished running, and here you can see in the batch gradient descent. So right now we are now comparing data set with, I think this is 1 to 10, 100. Okay, this is 1000, this is million, 100 million versus 1000. So in the large data set there are 100 million data points, in small data set there are 1000 points, and you can see that with batch gradient descent, which takes all data points into consideration, for small data set the final loss is 6, But for stochastic gradient descent, for small data set, the final loss is 10. So loss is higher, fine. For batch gradient descent, for large data set, the final loss is 12 and it took 78 seconds to run the iterations. And how many iterations are we running? 50 epochs. And but for stochastic gradient descent to execute, it took only 0.87 seconds, and the loss is much smaller. And this is exactly what I wanted to show you. And here you can see the so the final loss value, it's a bit, since it's noisy, don't trust this value. Like, okay, yeah, you just happen to get a final loss value which is, this final loss value which is lower than 12, but maybe if the epochs were higher, since the convergence is anyway noisy, you can't compare the final loss that much between stochastic gradient descent and batch gradient descent, but definitely look at the time it took for execution to reach similar levels of losses. Time was much smaller. So that's the difference between batch gradient descent and stochastic gradient descent. And actually this graph is not telling you the whole story. If you look at this graph, you may feel like, oh, this stochastic gradient descent looks like really bad because it's like completely fluctuating, whereas batch gradient is not. But that is not the whole story. The whole story is that the time it took for execution was a small fraction. I think it took only like 1/100th of the time. So this is why for very big data sets, stochastic gradient descent is much better to have instead of batch gradient descent, or at least use mini batch gradient descent. Don't use the entire data set. I have one more piece of code here to show the stochastic gradient descent versus batch gradient descent as a GIF. I'm not going to walk you through this entire code because I just want to show the final output, not not go through the code. But here you will see here we are assuming a quadratic loss function of this nature, x square. So gradient is simply 2x, dou by dou x. And here we have a GIF file which let's download. SGD versus BGD. Let's open this. I'll open this and show you how the animation looks like. So this is the GIF and I hope you can see it properly. So this the orange one is the batch gradient descent, which is slowly going towards the local minimum, the global minimum in this particular case. But look at what's happening in the stochastic gradient descent. Sometimes the loss is increasing, sometimes it's decreasing, but eventually after many iterations, it will have a tendency to fall, to come closer and closer towards the minimum. So this is the reason why, see, the loss can increase, it can again decrease. So there is a oscillating nature because you are randomly just taking one data point from the data set. So I hope this brings fairly good amount of clarity between the differences to you about the differences between stochastic gradient descent and batch gradient descent. Now let's go back to our notebook. The only conclusion here is that for big data sets, stochastic gradient descent is faster. And okay, I will not claim that it gives lower loss and can give lower loss. I don't think it's always guaranteed, but you clearly see that it's much faster, 100 times faster. So this brings us to the end of this lecture. Just to recap, what we did in this lecture is we looked at one of the 4 methods that we are going to cover in the 4 separate lectures to make the gradient descent better. So we were making the gradient descent better in this particular lecture through stochastic gradient descent. In the upcoming lectures, we'll look at 3 more methods. But let me take a moment to appreciate you for reaching all the way till this point in this course, because there were several lectures that you had to cover. But I'm sure you are getting more and more command over the basic fundamentals behind machine learning, and I'm pretty sure you are laying these foundations brick by brick. I hope you are enjoying these lectures, and I hope to see you again in the next lecture. Take care until then. See you. Bye.